comparing two proportions in class portion of the notes. Is yawning contagious? According to the popular show Mythbusters, the answer is yes. In the March 9, 2005 episode, the Mythbusters team presented the results of an experiment involving 50 subjects. All of the subjects were placed in a booth for an extended period of time and monitored by a hidden camera. 2/3 of the subjects were put in the treatment group and given a yawn seed by one of the experimenters. That is, the experimenter yawned in the subject's presence prior to leaving the booth. The remaining subjects were put in a control group and given no yawn seed. What were the results? Well, of the 16 subjects in the control group, 4 yawned, and of the 34 subjects in the treatment group, 10 yawned. Adam Savage and Jamie Heineman, the co-hosts of Mythbusters, used this 4.4% difference to conclude that yawning is contagious. But the question is, what do you think? Well, I think maybe, because 4.4% is not that big of a difference, it could have just been due to randomization variability. They happened to put the people that are more likely to yawn in the booth with the yawn seed. There are 3 ways we could figure out if this difference is caused because yawning is contagious, or if it could just be due to randomization variability. The first way to check would be to do a simulation, which we don't do very often if we know how to do other things, but we could. The second way to test would be to do a hypothesis test. And the third way to test would be to do a confidence interval and see if that difference is above 0 or likely to be above 0. Let's talk about how we would do that. Well, in most cases, we do not calculate p-values with a simulation. Just like the inferences for the difference of means depend on the distribution of this difference of sample means, inferences for the difference of proportions depend on the distribution of the differences of the sample proportions. When taking samples of size n1 and n2 from 2 populations where the true proportion of successes are p1 and p2, the distribution of the difference has the following characteristics. And basically, this goes back to our random variable unit, which means if we need to subtract averages or find the mean average, we just subtract the 2 proportions. And then if we need to find the new standard deviation, we take the square root of the individual observations standard deviation squared, or variances, and we add them because either way we're adding variation. And then of course our standard deviations for proportions are given by the square root of PQ over N. So this formula. We also have to check conditions. Okay, again we need that N times P and N times Q are greater than 10 for both sets of data or both proportions. So this is what we've been doing over and over again. And if you need to go back and look at the old notes. Let's try to do 5 steps for this test on yawning. Well, at first glance it appears the proportion of people who yawn when given a yawn seed, so P being the true proportion, is greater than the proportion of people who yawn when not given a yawn seed, since the difference is greater than 0. However, it is possible that the true proportions are the same, and we got a difference this large due to randomization variability. To decide, it will conduct a 2-sample z-test for the difference of proportions with an alpha level of 0.05. So very similar to what we did with the difference of means, but this time we're using proportions and the conditions for proportions. Now we're going to go ahead and state our hypotheses. Our null hypothesis is that the difference is actually 0. There is no difference between the two. Showing somebody a yawn didn't cause them to be more likely to yawn. And our alternate is that the yawn seed was effective, and so the difference was greater than 0. We're going to check our conditions. Okay, it says the treatments are randomly assigned. It was not stated, but we're going to assume it, being that they were trying to do an experiment. Okay, and also that the sample sizes are large enough. Well, n times p hat 1 which let's go back and just make sure you understand what that is. So for the control group, 25% yawned, but we're looking at p hat of t, so the treatment group. 34 subjects in the treatment group yawned. So that is 29.4%. So if we wanted n times p, or n of treatment times p hat of treatment, well, there were 34 subjects in the treatment group times 29.4% that yawned. And that is where we get this 10, or it's actually 9.99, but it rounds to 10. Again, this was the 34 people in the treatment group times the 0.294% chance, or 0.294% proportion that yawned. We also do that with those that didn't yawn in the treatment group, those that yawned in the control group, and those that didn't yawn in the control group. Now, not all of those are greater than 10, unfortunately. This one's not. So again, we have to proceed with caution. Okay, now we're going to go ahead and do our calculations. The pooled value is a combination of n times p for the treatment group and n times p for the control group, divided by the total number of people in both groups. But we're not going to worry about pulling it by hand. We'll let the calculator do that for us. In fact, when the calculator asks you if you should pool, say no, because the only time we want it to, it won't even ask. It'll just do it for you. So our calculations are actually going to be given by the two proportion z-test. And let's go ahead and do that to make sure you understand. Go to the test menu, go to two proportion z-test. Our first group was the treatment group, and we had 10 of the 34 people yawn. Our second group was the control group, and we had 4 of the 16 control group people yawn. We're curious to see if the treatment group had a greater proportion than the control group, so we're going to pick this one, and we're going to ask it to calculate. And here are our results. I'm going to write this down. I went ahead and wrote everything down from the two proportion z-test in the calculator. I got my z value, which would be our standardized value, and that would come from the difference from our samples minus the hypothesized difference, divided by, and here's the pooled information. Our data told us that the treatment group had a difference of 29.4%. Our control group had a difference of, or not a difference, excuse me, a proportion of people that yawned of 29.4%. Our control group had a proportion of people that yawned of 25%. And the pooled, which would be somewhere in between the two, given by the formula above, is 0.28. And the calculator did it for us. So you could plug that in to the z-statistic formula if you wanted to, and get this z value. But again, we can get it out of the calculator. And using that, what we're actually saying is what's the probability of getting a difference between the treatment group minus the control group being greater than or equal to 4.4%. And that's the same as the probability of getting a z-score greater than 0.3241. And in this case, that's fairly likely, which it doesn't surprise me because my z-score is not that far away from 0, 0.3729. I'm going to change that to percent to make sure that makes sense. So that is for a percent. And that is a fairly high probability, so it's not that rare. And so since that value of 37.3729 is greater than our alpha level of 0.05, we fail to reject and cannot conclude that yawning is contagious. Now, I swear I have read somewhere that it is. If I see it on TV, I yawn, but statistically, this sample was not good enough to convince me. Maybe they need to do it again and again. The other thing I did with the difference of two proportions in class was discussing the drug Plavix versus a new drug, the new drug Plavix versus the standard treatment for patients, that suffer minor heart attacks. And we went ahead and found a confidence interval for that. Let me read the setup just in case. Drug held for treating heart attacks. In a study of 12,562 patients in 28 countries, half the subjects were randomly assigned to a new drug called Plavix, and the other half were given the standard treatment for patients who suffered minor heart attacks. Just 9.3% of those receiving Plavix had further complications, compared to 11.5% of those receiving the standard treatment. Use a 90% confidence interval to estimate the true reduction in the proportion of patients with further complications. And then the big question is, does my interval give evidence that Plavix is more effective? So we're going to use our regular 4 steps, but first we have to define everything. P of P is the proportion of further complications with Plavix, and P of S is the proportion of further complications with the standard treatment. And then based off of our study of 12,562 patients, P hat of people that took Plavix was 9.3% who had further complications, while the standard treatment, more people seem to have further complications. So the difference, if you did Plavix minus standard, is negative 2.2. And since we're looking at further complications as a bad thing, negative 2.2 is kind of indicative of the facts that it looks like Plavix is better right now. But we're going to check to see how likely it is that our actual mean is negative. Okay, so we're going to do a confidence interval surrounding negative 2.2. So step number 1, we are trying to estimate the true difference in further complications. It appears that it is negative 2.2, but this is probably incorrect, so I will conduct a 90% z-sample confidence interval to check. Probably incorrect because our likelihood of getting it right with a point estimate is teeny tiny. We check our conditions. The treatments were randomly assigned, and we assume that 12,562 is less than 10% of the population, and so is half of both of those. And actually, I should have this as being 6,281. The Plavix people, that's less than 10% of the population, and the non-Plavix people, that's less than 10% of the population, and that makes it independent condition. We also need to check the NP and Q, and if we do that, we can carefully show work. The number of people who took Plavix and the proportion that had further complications gives us 584, which is greater than 10. The number of people who took Plavix and proportion that didn't have further complications also gives us another greater than 10. We do the same thing for the standard treatment, and all of those are greater than 10. So it means that's our approximately normal condition. It looks like our sampling distribution is approximately normal, and if it's approximately normal, then we can go ahead and use a z critical value and try to figure out a confidence interval. Again, a confidence interval is given by the difference plus or minus the margin of error, in which case is given by z times the standard deviation. And the standard deviation is given by the proportion of people who had further complications of Plavix times those that didn't, divided by the number of people that had Plavix, plus same thing with the standard treatment. Again, we can just go ahead and use the calculator for this. So you're just going to use a 2-sample z interval. And if you do that, you get negative 0.0309 to negative 0.031. And that would give us our step number 4, which is that I am 90% confident the true difference between the two drugs is between negative 0.0309 to negative 0.013. Therefore, I actually think Plavix did better. I will clarify this on the second video.